We've seen in great detail how the adjacency matrix, adjacency list, and the adjacency set implementations of a graph work. Now we come to the point, when do we use one representation over another? What are the advantages of using an adjacency matrix, say against using an adjacency set, and the other way around as well? Now, there are specific instances where certain representations work better. And let's take a quick look at a comparison between the adjacency matrix and the adjacency list or the adjacency set representation. Here we club together the adjacency list and the adjacency set because overall their representations are very similar. It's only a small difference. The adjacency matrix representation of a graph works extremely well when a graph is well connected. And by well connected, I mean when there are many nodes in the graph which are connected to many other nodes in the graph directly. If there is if there are a huge number of edges in the graph where a single node can be connected to many other nodes, then an adjacency matrix representation is the most efficient and your best bet. If you think about it, an adjacency matrix, when the number of vertices in your graph is V, requires V square space to represent all those vertices and all the interconnections between the vertex. This extra space is only justified when the number of connections are very, very large. So you typically use an adjacency matrix representation when your graph is well connected and has a huge number of connections. The converse is also obvious. If you have a sparse graph, that is, which has few connection between the nodes, then this is most efficiently represented using an adjacency list or an adjacency set. A sparse graph is one which has very few connections between the vertices. If the number of connections are small, and of course this is subjective, what you mean by large number of connections or small number of connections, that's the decision which you have to take as an implementer. A sparse graph is, however, more efficiently represented using an adjacency list or an adjacency set. This does not have the overhead of V square space being allocated upfront to represent the connections between vertices. You'll only add one node to the adjacency set or list of another node if a connection actually exists. This is what makes this representation efficient. Let's now see a quick comparison of common operations across the adjacency matrix, adjacency list, and the adjacency set. Now let's assume that E is the number of edges that are present in a graph. So we are representing the same graph across all three implementations. E is the number of edges and V is the number of vertices. The efficiency of all the operations we performed will be measured in terms of E, the number of edges, or V, the number of vertices. So let's see. Let's see the operations and the efficiency metrics we are using to compare these three. The very first thing is, how much space do these representations occupy? So we'll be measuring them along the axis of space. We'll also measure how long it takes to perform the is edge present operation. Say we are given one vertex and we want to see if there is an edge present from that vertex, say V1, to another vertex V2. How long does that operation take? And lastly, we want to compare how long it takes to iterate over the edges on a particular vertex. So we know the vertex V that we are interested in. How long does it take us to iterate over all edges incident on that vertex? Let's start with the adjacency matrix. It's very clear based on the representation is that if we have V vertices, the space required to store the adjacency matrix is V square. V rows and V columns. V square space is required. Now to check whether an edge is present is very, very fast. It takes constant time, order of 1, to check whether an edge is present from vertex V1 to vertex V2. It's a simple lookup into the adjacency matrix. Again, very straightforward. Now, if you had to iterate over all edges on a vertex V, it would take you V time. This is because you'd iterate over all the cells in that particular row and check whether one was present in any of those cells. So you'd have to look at all the V cells in a row, and that's why it takes you V time. That is the complexity. Let's see how an adjacency list performs. The space requirements for an adjacency list representation is E plus V. This is because every vertex is a node, so that accounts for the V space, and every edge is represented by another vertex in the adjacency list of the vertex that it's connected to. This means the space requirements for an adjacency list is E plus V. If we had to check for whether an edge is present between vertices V1 and V2, the time complexity of this operation is order of degree of V, where degree of V is the number of edges incident on V, or the number of edges that V connects to. This is because we'd have to iterate through all the vertices on the adjacency list. We'd have to go through it one by one and check whether V2 is present in the adjacency list of V1. That is why the complexity is order of degree of V. And lastly, the time complexity to iterate over all the adjacent vertices of any vertex is degree of V. So that means the time complexity to iterate over edges on a vertex is again degree of V, where V is the vertex and degree is the number of edges that are incident on that vertex. Let's see these metrics for an adjacency set. The space occupied by an adjacency set representation is exactly the same as an adjacency list representation. It is E plus V, where E is the number of edges in the graph and V is the number of vertices in a graph. The difference between an adjacency list and an adjacency set comes in the time complexity to check whether an edge is present between vertex V1 and V2. If you notice, an adjacency set representation is much faster in performing this check. The complexity is order of log of the degree of the vertex V. The order of log of the number of edges incident on V is the time it takes to check whether an edge is present. What's the reason for this difference? A list is simply a list. We have to iterate through all elements to find whether it contains a particular element. In the case of a set, we can have a much better implementation. Maybe it's a binary search tree, for example. A set can be implemented as a binary search tree, and in that case, to look up a particular element in a binary search tree, the time taken is log of n, where n is the number of elements in the binary search tree. So a set representation of adjacent vertices is much more performant when we are trying to find whether there's an edge linking one vertex to another. And lastly, the time taken to iterate over the edges on a vertex is the degree of V, where the degree represents the number of edges incident on the vertex V. Exactly the same as in the case of an adjacency list. This table can be a quick lookup for you to figure out what representation is the best for you under all the circumstances. Which operation is it that you want to be fast? Can you trade off space with the efficiency in looking up a particular edge? These are the factors which go into your decision of whether to choose an adjacency list, adjacency set, or an adjacency matrix representation of a graph.